So, sound check. Stefan, can you hear something? Does it work? Hand sign, please.
No hands, and I can't hear you.
Jetzt? Test 1, 2, 3. Wink mit der Hand, wenn es geht. Super.
Sehr geil.
Gut. Sets the mute settings of Windows 11. Now we know. So, can the stream hear me? Does the microphone work? La 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 la. Test 1, 2, 3. Hello from Vienna. Good. Stream can hear me. So then let's get started. So. Hello everyone, welcome to the February 2023 meetup of the .NET Meetup, as always presented by us, .NET Devs.at. Who we are a non-profit organization about sharing .NET knowledge, providing space to share it. You can find us nearly everywhere, YouTube, we have a Slack, Twitch, Twitter, Zoom, Mastodon, and behind this nice QR code you find everything. The stream gets the links in the chat. And yeah, thank you all for joining here in person and also on stream. And also I want to thank our sponsors. And the first sponsor I want to thank is our location sponsor today. So on stage here, there's the mic.
Hi everyone, so nice to have you guys here. We at Square, we love hosting these events and getting to know new people and new communities. We are a software development company, technology agnostic. That's why we wanted to also host a .NET event to show that we also have developers and projects in this area. Yeah, looking really forward to meet all of you guys after the talks. We have a guest book here on the wall, so if you have any feedback for us today, please feel free to leave a review here. Yeah, and if you haven't already, follow us on the meetup group so that you can see all of our meetups that are coming up. For the organizational stuff, we have 3 restrooms, one here, one at the entrance area, both are unisex, and one women's restroom back to the left. And after the talk, there will be food and drinks. Help yourself to everything you find in the kitchen. And yeah, that's all from my side. Thank you all for coming. And now the stage is yours, Paul and Raffael.
No. I still have to say they have 2-3 minutes left.
I'm so sorry. Have fun, guys.
Thank you for hosting us. We also have other sponsors that I need to mention. So thanks to Rubicon and Tietery for sponsoring financially. With that, you can buy the hardware for streaming. That also remote people can watch. And also thank you for JetBrains for sponsoring. They are sponsoring us with a giveaway. We have today 2 12-month product licenses to give away. One for the streamers, one here at location. And for the streamers to take part in the raffle, somewhen during the talk, type JetBrains in the chat, and at the end we do the raffle and see who wins them. The people in the audience, please don't take part. Don't take part in that. That's for the viewers on the stream. You have your own license. Good. Some quick news from the community. Our meetup is part of the .NET Foundation. And the .NET Foundation has this virtual user group meetup where a lot of .NET meetups around the world are announcing their events. So if you're running out of .NET content, you find a lot. And yeah, I forgot to put the date on it, but I think in May there's the Global Asia Austria event again happening. Yeah, that was some quick. We make us now also content recommendations for additional content. So one recommendation is our own Stefan, who's doing live streams about .NET topics. Still source generators, or? No.
.NET tools.
.NET tools this time. Cool. Then we have Claudio Berlusconi, a Swiss content creator with entry-level content, and also we can recommend big jobs as doing more architectures, more high level, more 200, 300, level 300 content. And with that, now it's time for Paul and Raffael. So we have a quick technical switch here with probably some problems. No. Good. Your stage, Raffael.
Super. So, welcome to our talk. It's called Real-World Distributed Systems with Microsoft Orleans. Grains for the win. That's the important part of it. Before we go into the details, we would ask you to ask your questions anytime they come to your mind. Stefan will be so nice and also check what's going on in the chat online. So if there is an interesting question coming up, he will jump in as well, so that we get a kind of maybe an interactive part of it. We were starting off with a kind of a background theoretical part and then go into a demo. Let's leave away all the adjectives. It's gonna be.
It will be awesome. Just don't want to set the stage, but it will be cool.
Okay. So who are we? So my name is Paul Rohorzka. I consider myself a software gardener because I like the term. I like to plant software systems and sometimes cut away things that are not so working so well, and that's what I consider is a good metaphor instead of thinking about, are you a senior, a lead architect, or just beginning? I'm a gardener, I liked it. And I really have a strong focus on maintainability and quality and testing of code. And this is my awesome colleague.
Awesome. Welcome, guys, also from my side. My name is Raffael Rehberger. I'm a software developer at Fronius International, joining today from Austria. So I'm not usually from here, but happy to be here, actually. And I'm a huge FLOSS enthusiast in general, so everything that is free, libre, and open source is where my heart lies. And the reason why we came here today, basically, is because we like to talk about distributed systems. And we had been discussing how can we get best into the talk. And how can we get best into a topic? Well, we have to tackle history. That's what we have to do. So let's jump back into the early beginnings of the active world. And we have to jump back actually quite far back into history. We're talking about the year 1973. Yep, sounds confusing, but just to get you on board, how did things look back then? We had computing that was quite big. So we have this lovely storage cluster here, which only had a rock solid size of 280 megabytes, which was probably as big as this room here, just for comparison sakes. And then we also have this RAM board, so we have this RAM disk, more or less, 10 times 10 centimeters, and only an astounding 1 kilobyte of RAM. So the state of memory wasn't that particularly good back then, but we had one development that was really cool because we got into microprocessors. And with the Intel 4004 back then, Intel released the first commercially viable microprocessor. And with microprocessors, we had a very interesting development because we were first challenged with the problem that we cannot really fit too much functionality on this. Just to give a little bit of perspective there, this is a 4-bit data with microprocessor. So 4-bit, if we just want to add 2 numbers, that effectively takes 4 cycles. So it's not particularly fast, and that's why engineers back then had been challenged with coming up solutions. And back in the year 1973, they already had to think about distributed systems. And one man that we are talking about today, or actually the concept that he developed, is Mr. Carl Hewitt. Sadly died in the year 2022 in December. But in the year 1973, he wrote a paper about universal modular actor formalisms for artificial intelligence. Artificial intelligence in the year 1973, just saying. Yeah, and he was a very smart head, and he developed this actor concept that we're going to talk about today. And yeah, of course, as it is, he is coming from the MIT Department of Electrical Engineering and Computer Science. But now that we have a little bit of background and have a little bit of state in the art in the year 1973, let's discuss actors. What are actors like?
Super. When we think about systems that get messages from different sources, then we have usually different challenges that we face. And one of the challenges that we usually face is that we have to deal with the concurrency of incoming messages. So we have our system and many other systems are sending messages to us, and what do we do about this concurrency issue that might come up at that point in time? And one very usual solution to this is to put a queue in between. So for some people, that's the solution to everything. Got a problem, put a queue into it. Still works. And the thing is, then if you have this queue in between, that means that on arrival, the queue will somehow, in some way, queue up. So one will be the first and the other will be last. And then the system on the other side can decide in what manner the messages that are now sequentially within the queue can be processed. And that's basically one of the important building blocks of an actor. So an actor is a system that has different purposes and different properties, and one of it is that it has a queue in front of it, and that's the so-called inbox. So all the messages that you send to an actor goes to the inbox, and then the actor can work on the messages in that inbox. And the thing is, with an actor system, you usually get the guarantee that the execution of the code that is running within the actor is single-threaded. So you don't have to care about concurrency in the code that is running in the actor. And that's, of course, a very good idea, because then you don't have to care about all of the problems that you usually have if you think about multi-threaded systems with all the problems that can come up here. As a concept, you can think of an actor being combined of three things. So one is the type of the actor. So what's the thing that it is doing? And it has to have an identity. And this identity can, for example, be a type in a statically typed system. That could be one part of the identity. And you could attach a string, let's say, to it or some other data, and it could be kind of a username, for example. Then you have a thing that is describing what is the actor actually doing. So that's behavior that you have on the actor. And optionally, you could have a stateful actor. So there could be also state within the actor. And as we have the state that is just local to the problem that the actor is supposed to solve, and we have a single-threaded execution, that is not a big problem to have already some state somewhere, because somewhere in the system we have to have the state. Okay, so, but the question now might be, okay, but how do we distribute load? Because a single thread is nice, but if all the messages have to queue up and there's a lot of it, then we have to do something about it. And the thing is, okay, then we just have to fan out. So with an actor-based system, it's usually very easy to spawn a lot of actors and to distribute the load that you have to process to the many difference that you have spawned up. And the actor framework is, so one thing that the actor framework can do to you is really to make this pretty nice and transparent to you to spawn up new instances as you need them. Okay, so what does an actor framework do? An actor framework cares about the actor's lifetime. So if you want to send a message to an actor, the actor framework takes care that the actor on the other side of this calling process is actually there. So if you need it, it will be there. That's one of the guarantees of the actor framework. Another thing is to manage the actors' inboxes. including all the problems, what happens if the actor cluster goes down and if you spawn it up again. Have you lost everything that might be in your inboxes? The actor framework could probably care about this. It could care about the persistence, so it could care about what to do with the things that you might not only have stored within the inboxes, but also in other things. So what time of the life cycle of a grain, for example, do you read data from a store? Do you write back data to a store? It cares about the message delivery. So how do the messages really come across from one actor to another? Because as we will see later, actors can be next to each other within the same process, or they could be running in the other part of the world, in another data center even. And the actor framework can take care of all the heavy lifting to have this communication still going, no matter what it is in between. Of course, it cannot hide latency, for example, but it can really ease the pain of the communication and programming of this communication. And one thing that is, of course, also important, things go wrong. And in real world distributed system, things go wrong all the time. So the errors will occur, and that is also an important part, that the errors get propagated properly. Okay, so what messaging patterns do we usually see when we're using actors? For this to understand, we have to think about what can an actor do. An actor is pretty, and it's one of the beauties, it's pretty simple usually, or pretty dumb, you could call it. So what can it do? It can create another actor. It can say, for example, I need to talk to someone, please create it to me, or give it to me. It can send messages to actors, either actors it created itself or actors that it knows about, by its address, for example. And at the end of the communication, if the service of another actor is not needed, it can decide or tell the actor framework to be there for garbage collection, basically. And the details, of course, depend on the system that you're using. So there are several systems out there. They have some similarities in the concepts, but also in the details, of course, some differences. But basically, that's the idea, what an actor can do. If you create an actor, then you, as we already said, we can take the work that is coming to an actor, and the actor could, in runtime, decide to fan out this work to other actors. It could decide to do it locally. It could decide to span out to other actors. That could be dynamically or statically programmed. So you have the possibility to really use this leveraging of multiple instances to distribute the loads that you have to work on. And the thing is that it's really cool that you have a system that on the one hand allows you to have very simple things. So you can think as an actor in the size of a class. And it can be a really simple, small class fitting on a screen, maybe, the code of the class. But still you can think of it as being a completely separate service, because it could be running on another data center, which is you can just talk to it without any problems. And that's the beauty of it, that you can really stay focused on what is the thing, what is the responsibility that is in this actor. And that's really cool. Okay, yes, one thing is, of course, lifetime. So when we spawn actors, they take up resources, they take up memory, they might take up CPU load. And if we spawn a lot of them, so case of or millions of actors, sometimes they might get obsolete and the system will want to get rid of them and dispose them. And that's also something that the actor framework can take care of with the help of the programmer of the actor. Okay, if we send messages to other actors, then it's totally transparent, besides of things like latency, but from the programming model, it's totally transparent how the grains are separated to each other. So as said, you can have all the things in a single process. That could be a thing, or you can really have a globally distributed system. So a system where some actor is running in a data center in Frankfurt, for example, and the other is on the other side of the globe. And still they can communicate with the same messaging patterns, the same programming APIs to be used. And it can be a thing of configuration of the system, how the system is actually split. Yes, and of course, a lot of things have to be considered with all these complexities, but usually you don't have to care a lot about those complexities. These are managed by the actor system. Okay, there are two different communication modes that you want to consider. So one is where you want to just trigger another actor to do something, but you do not really care about how is that going, what you asked the actor to do. So that would be the tell metaphor. So you tell it, do something, write an email, whatever, but I don't wait for your answer. I don't care if it's working. That's another concern. I do not care about it. On the other hand, you could ask an actor for something because you need an information as an actor. You need an information to continue in your processing, and you need another actor to do something for you. And so you, of course, have to somehow wait on the answer. So that would be the ask principle, the ask metaphor. And that's basically what we also have in typical HTTP communication, a kind of request-response communication. Okay, then.
Now that we have seen how actors in theory work in standalone, they usually don't come along in a standalone mode. So we usually have a system out of multiple actors playing together. Let's have a look at the first usual setup. So whenever you're seeing an actor framework in the real world or an actor system in the real world, we usually don't directly communicate with the actors. Because sometimes, for frontends especially, it can be quite daunting to put messages into a queue. And effectively, they probably also want some response guarantees at some point. So what we usually tend to do is we put frontends in front of them. Something like REST APIs. We have API gateways that can remote into the system of actors with websites, or even microservices could be used to integrate into a system of actors. Right, and in the system of actors, we are very flexible in the way how we wire these grains together, or how actors can put messages into the inboxes of other actors. And optionally, as we've already heard, an actor can hold state, and when it basically terminates or activates, it can persist its state to some storage layer, so some kind of storage tree, something like a database or a Redis. And if the grain starts up again, or the actor starts up again, it can load all of its state back from the persistence layer. Good. Now that we have seen how a typical setup looks like, we should probably also talk a little bit about the concurrency thing that we have in actor models. So we have this saying here, concurrency in the actor model is achieved through messaging. Let's think about this for a moment. So we have learned so far that actors are communicating through messaging. Messages that are put into the inboxes of receiving actors. The actor itself can only pick up a single message at a time. And it is a crucial point and aspect for the whole system to actually work out and to be concurrent. Messages are always passed by value. So there's no actual way how a message can be manipulated effectively. So we don't have any shared memory in that regard. A message is something that comes in from the queue and we cannot manipulate it. And then the best practice there obviously is also, since it could be that actors are running in the same grain and we could abuse that mechanism, that we make sure that the object that we're passing through the memory is also immutable. But again, the most important aspect is that the recipe that is acting on this message that is incoming into the queue is executed purely sequentially. That means we're not allowed to use any multi-threading. We're not allowed to use any kind of multiprocessing. If we would do this, we would break the concurrency paradigm there.
I have a question. Okay, so we have state. So obviously any kind of multi-threading, multiprocessing would potentially lead to all kinds of problems, race conditions. However, what if I use a functional paradigm to implement an actor? Is that possible?
That is
Because there I could safely parallelize as long as I'm purely functional. I don't run into these problems.
absolutely. So those paradigms don't conflict with each other. If you're a functional programmer and you're aware that you have a synchronization point and the recipe that performs an operation on that message is at some point terminating, it's completely fine. But you should be aware that if you are sending messages in a parallel way to another system, you might change the order of the overall system.
Yeah.
So that's the aspect
side
there.
effect, yeah.
Yeah.
This is not the main reason, so that you want to have these ordering guarantees, and then you lose when you don't sequentially kind of process the queue. As long as you start to multi kind of batch those things which are counting by the queue, you mess up the ordering, right?
Exactly, you mess up the ordering.
That's
Even though
why-
that's also something we want to really appreciate as developers of such actors. So we shouldn't assume any kind of ordering of messages.
For some use cases, I mentioned it's actually useful to break out of this sequential concurrency limitation, because as soon as you have state on an actor, of course you interact with it, so it changes state. But on the other hand, you also want to read back state. So for that kind of operation, I want to query the state. You would allow for the query operation at least to do this parallel to what the processing operations do, so that you don't have a bottleneck by read-write operations that are blocking each other.
Absolutely. Even though I would still say that best practice is to keep asynchronous, or let's say threaded or multiprocessed actions out of the loop as much as possible. Because these things start to turn to side effects that later on will hurt you at some point. So also the best practice of Microsoft or Leans give you the guidelines to rather make them really synchronously.
And I think also, as you showed on the previous slide, usually your whole system will not be just that actor-based system. There will be other things to it, and things to where you could put payload to it if it's a better fit to make it in a parallel multi-threaded system. So it's totally fine for the actor system just to be part of a bigger system where different paradigms are working together. Oh, a question from the chat.
So Sebastian has a tough time imagining what the actor-based system does. What does one agent do? Is it a complete use case, or is it just a part of it using choreography to collaborate with others?
It is basically a very small subpart of the problem that you try to solve. So it is basically not a full thing, as Paul already mentioned. It's very scoped, and it's very, there you are in the camera, hello. It is already very tight to a single purpose, really a very small use case that the actor is fulfilling. And the real, let's say, complexity solving is happening by actually combining multiple actors together and make them perform something like an orchestra. Awesome. Then let's move ahead. So we have been discussing global shared state already, and I think we can all agree that global shared state is a bad thing. But luckily, if we follow the rules that we had beforehand, we are in a lucky position that we cannot even get into this place. So the only way we can actually share some kind of state is through messaging. Messaging that contains some state modification that is performed once again sequentially. But whenever we do share state with this mechanism, we need to be aware that we don't have any guarantee of message ordering, is where we come back from. And also, we don't effectively have a guarantee of immediate answer. Since we have a queuing system in between, we as a caller that is sending off a message cannot really know how much messages are already in that queue. So, and jumping on this board, we again said that global shared state is bad, but we have also the possibility to hold state inside the actor, and also Paul has already previously outlined this. Actors are luckily singly threaded. That means whenever we're processing a message and want to perform a manipulation on that state that is held inside the actor, we are guaranteed to be fully race condition safe. So we are synchronously accessing this memory and can manipulate that memory. And if we, for example, like you mentioned, would do this in some kind of asynchronous manner with threading and multiprocessing, we would basically lose this kind of benefit.
Immutability is key there to prevent this.
Absolutely. Yeah, but nonetheless, when we do this, we need to ask ourselves the question, do we really want to persist that state? Because what does it mean when we persist state in an actor? That means we have to take care what happens if the actor, for example, terminates and starts from the green, basically. So without any state. Will my actor still work? What is the expected behavior when my actor is reset by the actor framework? Does my actor actually handle this situation? So these are the questions that we should ask ourselves if we're using shared state in actors. Yeah, and then one, let's say, a little bit more advanced topic is the topic of resiliency. So what we can achieve with having a look at an actor system and having the idea in mind that an actor basically consists out of an inbox and a sequentially running code that is basically operating on a message that is incoming, we can make the simplification that the whole state of a system of actors lies within the queues, so within the inboxes of these grains. And if we, for example, make a snapshot at any point in time, where we really back up every content of that queue, we effectively get the possibility to create snapshots at point in time that we can restore and continue operation as if nothing would have happened. Another thing that is only possible when we follow this paradigm of running everything sequentially. Yeah, and this could be, for example, quite helpful if you're really interested, for example, in dumping something from a productive system and testing it for local host testing.
In this case, if you have a shared, so if you have an actor state now, right? How is this hydrated, this actor state? Is this lost if the actor dies and restarts again, or will it be hydrated based on the previous state, or will it be hydrated based on the inbox? What is the process done here?
That really depends on how we would implement that actor. So if we are aware about the situation that our actor needs to restore from, let's say, the persistence, what this previous state was, then we have to implement this particular logic into that actor. That as soon as the grain or the actor is reinstantiated, the memory or the state is pulled out from some persistence layer. If we don't do this, by default, we just lose the state, and we need to be aware about the situation.
Yes, but one of the beauties is that usually the actor-based system gives us just a layer, so we just have to hook into it and make sure that we, in the right point in time, we write back the data if we have changed significant data, and if we get activated again, that we read the data, but it's totally transparent to us where the data actually is.
Okay, so that's similar to Akka, right? Where you can
Exactly.
Yes, exactly, absolutely.
So
and this is then in the background also stored as kind of an event senior, right? These state changes are obviously.
Well, it depends on the persistence mechanism that you're using.
And if you're talking about frameworks like Microsoft Orleans, you're really flexible to use whatever you want. These are more or less hooks or lifecycle hooks that you can just implement yourself. And as soon as the framework is instantiating an actor, it's making sure to call that hook, and you can implement your own logic at this point in time.
Is this what happens if an actor crashes? With the message that it was processing, we put back into the inbox, and when the actor is revived, will the actor process it again? Or
in the case of Microsoft Orleans, that is not the case, so the message is lost in this case. But actor frameworks, for example, like Akka, have sometimes different ways of handling this.
But is the message auto-acknowledged as soon as you read it from the inbox, or do you have a way to acknowledge it, once you processed it?
In Microsoft Orleans, I think we don't have any possibility to use the auto-acknowledge, it's just happening. So we don't have any means to configure that at this stage. In Akka, the concept of the queue and the actual recipe are a little bit more present, and you can actually implement the behavior on how the queues are pulled. And then you could be implementing some logic that you put the message back in case the actor crashed for some reason.
But doesn't what you just said contradict your claim that all state of the system is in the inbox? Because, I DQ a message, I crash, then that message is lost. So apparently the state of the inbox is not exactly the state of the system.
That really depends if the actor itself holds the state. So if the actor is resilient enough to be restarted again and just continue operating from where it started or stopped previously, then we don't lose any state in the whole system.
But can this really guarantee once you kind of acknowledge, as soon as you read this message from the inbox, you acknowledge obviously Orleans, right? And I don't know the details of Orleans. And when you kind of take this message, and even in the next millisecond, you would now put it to a persistence, right? So that it will not be lost if your actor crashes. But even in this millisecond, your actor could crash, right? So there's definitely no guarantee that you don't lose data if you're not able to manually acknowledge once you put it somewhere where it's persistently stored.
Right.
Yeah.
Exactly. The message isn't acknowledged when you read it from the queue. It's acknowledged when the behavior of the grain completes. If you throw an exception, it will not be acknowledged.
Okay.
So then you can opt in to retry behaviors, but by default, I think it would drop the message.
I would drop
just
the message.
take the next one. But you could do retries, so you have some control over that as well. But the last operation should be persisting state before you finish the behavior, then you
Yeah, I think this makes sense because everything else would be kind of very unique, right?
So just one more question. A grain is an actor.
A grain is an actor, yeah. We're leaking this vocabulary too, and we will use it interchangeably. Grain is the term that Orleans uses for an actor.
We have some more questions in the back because I see some thoughts on the end.
I just wanted to ask if there's the concept of a dead letter queue in Orleans.
Not that I know of that it's built in. You can probably implement it yourself in the grain if you want to, that if a message for whatever reason is not processable, that you have some other grain that takes care of requeuing it at a later point in time.
You can do grain to call filters that intercept before or after grain calls again. And this middleware could handle it, but I think it's not out of the box.
Out of the box, there's nothing.
Do it yourself, I guess. Yeah, okay. Yes, absolutely.
So, James trying to wrap his head around snapshots. Could you elaborate a little bit further on snapshots of queues?
So basically what we could do in the simplest case, as we've already heard this in the scenario, is using some kind of a grain filter. This grain filter could intercept all the messages and eventually just dump them away in some kind of persistent storage. That would be one of the most simple mechanisms that you can use to back away all the data in the queue.
And I think for all these questions, I think they're all very valuable, and I think we also have somehow to distinct what is the basic theoretical concept behind actors and the different implementations for go there for a specific part with all of the concepts. So, for example, if we're talking about akka, we mentioned it, it has some kind of a different behavior where, as Rafi said, the thing that you're talking to a queue is very clear to you because you really have to dequeue messages and you have to acknowledge on that. But when we're now talking, then we will then go to the concrete Microsoft offering for Microsoft Orleans. There are somehow how different ways how things are done and things are abstracted away. And so I would say in a typical Microsoft way, so it's super easy to use it compared to other systems. But of course, they, on some parts, they might be missing out on some super fine-grained details to control everything that you might want to have. Or you might have to take an extra step. So as you mentioned, for example, to kind of implement that letter queue for that. Yeah.
And I also think it comes down to how do you interact with the tell-ask principles.
Exactly.
If you have a system that asks for something and waits for a response, it will retry itself if it fails, so it doesn't get a response. If you just do a tell, it's probably safer to put the durable queue in front of it again, so that it's guaranteed to be processed at some point. So that's something that the framework unfortunately doesn't provide, but you can easily build around it.
Okay. Then let's jump into a brief comparison between microservices and actors, because apparently that is a very daunting question to people starting out with actors to get started with. And we've prepared a small table where we try to compare from the left side microservices with actors. And when we're talking about microservices, we have just one means to implement distributed functionality. Whereas in the actor world, what we're really trying to do is to create a model that allows concurrent computations. The distributed side effect is just positive side effect that comes alongside with the parallel computation possibilities. Then in microservices world, you typically fall back to using DDD, and we try to model the microservices based on a single bounded context. Whereas in the actor world, we're trying to go one step deeper. So let's make a simple example. Let's say we have a microservice that takes care of performing calculate operations, simple additions, subtractions, dividing, multiplying. then it would be perfectly fine for bounded context to bind this into a single microservice. In the actor world, however, we would go one step deeper and we would try to make an actor that is really taking care of the most granular operation, for example, adding two numbers. In the microservice world, we basically have two paradigms, I guess. We scale vertically and we do this with multi-process setup. So worker services, for example, consume something from a queue. If we want to scale that, we just increment process count and we have more workers processing that queue. In the actor world, we also scale vertically. However, we do this in a multi-partition way. So instead of having a dedicated process for each of these actors, we have a concept in between. We will be talking about silos, or in this case, partitions, that take care of hosting many of these actors. And one actor belongs to one such partition. And that means we just have one hosting process that takes care of instantiating an actor in itself. So the instantiation itself is very lightweight, and we have just one place where this actor lives. And if we want to scale, we would just create yet another partition. So if we see that one partition already has 10 million grains or actors living in it, then we could just add yet another partition. Right. In the microservices world, again, we have one similarity. We're trying to have loosely coupled architectures. So that's the overall goal that we try to achieve anyway. And just to again pointed out that it's very important that actors are supposed to be the most granular, most atomic operation available. We should really also think about them as a single sub-problem. So try not to model a single actor with too much responsibility, make it as small as possible, cut it as small as possible. And now we jump into the topic of virtual actors. And now we have been talking a lot of actors in general. And now we actually get into the world of Microsoft Orleans. So time to Orleans is forever, basically. Microsoft puts Microsoft Orleans as a cross-platform framework for developing scalable and distributed applications based on the virtual actor paradigm. So we had actors, and now we're talking about virtual actors. What is a virtual actor now? The question arises, I guess. And when we're talking about virtual actors, what we're actually talking about is virtual as in virtual memory. So these virtual actors can exist perpetually. That means they can be there or they can't be there. We have a guarantee at any point in time that if we address an actor with a message in the inbox, that the Orleans framework makes sure that it exists. That is the benefit of this case. And Orleans is basically capable of creating activations of actors and grains on demand. So we can also make the other way around when an actor is not needed anymore, because, for example, it has been idling for the last 6 hours, we can just remove it from memory again, which is a very nice mechanism, especially if we have millions of actors, where maybe one of these actors is just used once every hour. So the Orleans nomenclature, as I said, we've already leaked it through a little bit. It's very hard to not talk about grains when we're talking about actors in a presentation about virtual Orleans. So Orleans calls these actors grains. So it's again a virtual actor, and as we've already heard, they have to be single-threaded or should be single-threaded. And they can be distributed. So they can live in a single partition. We can have multiple partitions, and these partitions are what we call silos in the world. So the analogy, I guess, is clear. Farming analogy, we have grains live in a silo. And then we can cluster multiple silos together, and multiple silos then communicate with each other to identify where are grains locating. So they are basically gossiping with each other to see when an instantiation is happening and where in which of these silos the instantiation has been happening. And now we have already also talked about the grain lifecycle. Orleans has the following stages. So when we initially start up an actor, we're running into this activating stage. This activating stage is also something where we can hook in a lifecycle event into. So this is where we, for example, could implement catching all of the memory that we had persisted in the last activation run. Then, as soon as we've done this, we are in actual operation. So grain is active in memory and can receive messages. After, let's say, 5 hours, the grain hasn't done any work anymore, and Orleans just decides, hey, need to save memory, let's get rid of that grain. Then we are having a callback once again. This is this deactivation stage where we can basically dump away all of our internal state if we had any. And this is where we again restore from the persistence. So we have the grain life cycle. Right, then we're talking about grain transparency, and also we have been talking about this already, so we have been taking away quite a lot on the journey to this point. Basically, we as developers don't need to care where the grains are located. So we just need to know what kind of grain do I want, what behavior should it implement, and how can I address it. A simple addressing method could be by simply giving it a string as a name or identifier. We can use any kind of addressing method, but the only important thing is that I, as a sender of a message, need to know what is the identifier of the grain I'm wanting to send to. And the cool thing is we get complete transparency in terms of where these grains are located. We could be crossing network boundaries. So we could be talking with one silo and another silo in the US, for example. We could have in-memory communication. So we could be in the same silo, since the grain activation decided to be in the same silo. And yeah, we could just run on the same virtual machine as a dedicated silo.
Doesn't that make a lot of difference, performance-wise, for example?
Absolutely.
Is the framework clever enough to always do the right thing?
Of course, we have to help.
Yeah, absolutely. So I think it is certainly possible that you create, for example, a silo in the US and one in Europe, but you have to be aware at the end of the day that there's a few countries in between where the data has to travel until it reaches the destination. And also Orleans cannot defy physical laws, so you still have to be a little bit careful about the latency topic. That's nothing that Orleans can abstract away for you.
These silos, still another question. These silos are they always sliced across location means? I mean, because as you said, one silo lives in South America, another one lives in North America, and another one lives in Europe. Or is it also make to slice these or partition these silos differently based, for example, on, I don't know, user segmentation, right? That's also, so you, okay, so everyone cannot know kind of how to co-locate them because it's based on the domain how you slice the silos.
Yeah, so it's just a means of slicing, and you give them Orleans. This is basically the granularity that you give it to have it running somewhere.
Yeah, okay.
And what makes sense and what does not make sense depends, of course, on the problem domain.
So then you provide tags, or how do they then actually know to which or in which priority to go to?
So you can, in Orleans, it's called placement policies. So you can define placement policies where you give hints what things should be located together, for example, and what could be separated. Or you could definitely just really deploy it, of course, on another cluster and say this is part of another silo, and you say this is part of my cluster.
So you have to, in the addressing an actor, you need to take care of addressing the right actors. Right? So if the source actor is in Europe and you want the next actor to also be in Europe, then you have to address an actor that is in Europe, right?
No, it's another concern. It's another concern.
Okay.
So the communications, for the communication part itself, for the sending messages between actors, it's really transparent. So you just have to know the address and you send a message to it.
Okay.
And where that actor is actually living, that is depending on how you configure your system and how you deploy your system at the end.
Based on the placement strategy.
Based on things like placement strategies, for example.
Yeah, but let's say I have a system that is really distributed over the world, and I want my customers in Europe to be, my customer requests in Europe to be handled by grains in Europe for performance reasons, and my customer requests in North America to be handled in North America.
Okay, I see what you mean. Yeah.
And,
sure.
and so I need to, when I'm sending a message to an actor from a Europe grain, to send it to another Europe grain, right?
So usually, usually you would probably model it like this, that you don't care about location, for example, within the identities, you will stay within the same silo. And if you really have to explicitly cross the boundaries, you might want to really have explicit grains with explicit addresses that Senate that it's really running in the UK or wherever it's running. Good.
So the way you cut the silos is also probably very much related to how you shard and the state underneath, right? So if you are occasionally sharding or segment sharding.
Exactly. So it gives you another possibility to slice or shard your system, and of course it makes totally sense to also consider the data that you need for it and the way that you shard the data, and to put the silo as more or less a big part of the behavioral part of the system next to it. So there are different.
As well, then transfer of so the management of localized local silo data or state.
Pardon, I didn't get the question.
So do I have to take care of the state sharding that is aligned with silos underneath, or does the framework do that for me?
So usually, I think if I'm not mistaken, we do it per silo. So per silo, we can configure the persistence that we use, and for that, also the location of the persistence.
So you would have a persistence connection for a specific silo you're in.
Exactly.
And then you will have to address the synchronization concerns outside of the framework to make sure that if the actor changes silos, that the state somehow is still consistent, etc.
Well, you could have cross silo spanning mechanisms used by Orleans, but still you will probably you might not you might also need, besides all the framework niceties that you get from Orleans, you will usually, as I've also showed on the slide, have classical other components of the system to interact with. So for example, if this sharding of the data is really a very big issue, then you might have some other means to solve that issue and to really leverage that even from your system. So maybe to write a specific adapter to your persistence layer that you already have and that already works perfectly maybe.
And there is this grain persistence mechanism that Orleans offers, and you're completely free to implement your own grain persistence strategy, more or less, where this is possible. Okay. Then another question arises, of course, as we have been fanboying quite a lot about actors and Microsoft Orleans. When shouldn't we use actors? Which is
okay. Time is over.
Forget it. It's always cool. Okay. So as everything, it's of course not the problem to all of your the solution to all of your problems. Might impose another problem that you don't have if you use it in the wrong place. So things where actor-based systems might not be the very first thing you might consider. So if you have to carry a lot of data from one place to another and do something about it. So if you now have a big batch process that is going on and transferring the terabytes of data every night, maybe an actor-based system might not improve your situation very much. So let's be careful about this. If you have a problem where you might have an algorithm, for example, where different parts have to share memory, and that's the beauty of it, and that's the reason why it works so perfectly, then going to a system where you say, no, we don't share anything, but just we communicate with messages might not be an improvement as well. So also things that are really hard to parallelize. So maybe also from a theoretical point of view. So if you really have a problem that has to come, that has to really be processed in a typical multi-threaded system where you say there are giants, then it might not be the best idea to move to an actor-based system. Maybe, just a thing to consider. If you have a complex logic or if you need reaction time guarantees, because if you are used to have a system that is very closely knit together running within the same process, and you really can rely on everything, so if this process is still alive, then the process will do its work, so there's no questions asked, and there will not be latency or no significant latency between the parts in it, then going it and spreading it around and making some proxies in between and communication protocols that have to be serialized and deserialized might not help as well. So also a thing to consider. And then a last thing that we thought of is if you need a system where there's a lot of global coordination going on. So if you usually have a system where you at a very often point in times have to go to a single instance and coordinate with this instance, for example, to wait on other parts of the system to also communicate with it, an actor-based system might not be the very best fit. But it's a thing to consider, but always have in mind what are the trade-offs, because of course it's not a silver bullet at all. So some real-world examples. Let's go quick through it. One of the strengths, maybe that we managed to explain to you, is if you have a lot of things that can work pretty loosely coupled and independent of each other, then an actor-based system might be a good fit. And you could think of really making a system where every human in the world has its own actor. But, of course, maybe not a system where you need an actor for all of the, how many billion humans do we have on Earth, might have to need an actor activated at the same point in time. That might still be a problem, because that's a lot. And that might be too much for infrastructure, but it's totally fine to have a virtual, a perpetual actor that will be there if you have to communicate with it. So that could be totally viable. One question is it now just for the really big systems? And I think, of course, it shines on big systems, but still you can leverage some of the benefits even if you just have a single process thing. So it could be totally fine to just have a console app where you leverage internally the beauty of a programming model of actors. They could be totally fine. Or you could have this often cited multi-data center, super globe spanning system. And anything in between will be probably your system. Might not be that simple, might not be that globally distributed, but somewhere in between, I think, to consider. Yeah, and yeah, that's the one important, sentence here is what's really nice about it is that you get a lot of nice elasticity. So if your system moves from the left to the right, for example, you might not have to completely change the programming model. You have a means at hand where you can simply just add to it, so to work on additional load, for example. So one example from the real world, think about you have all over the world some hardware devices there. They are of different generations. Some are very recent, some are very old, some have different firmware versions, some have been online all the time, having the latest versions, some have been offline for years, and you have to somehow manage all those versions and the updates to these versions, for example. And there are things you might want to have, you have to consider. So for example, if you think you have a globally distributed system, it might not be probably the best idea to, within 5 minutes, all over the world, update all firmwares, taking down the whole system for 5 minutes, because it's just there, we can do it. Might not be the best thing. So maybe you want to update all those devices that are running in America, or you update all the Model X devices, or you update all the devices that haven't been online for a long time because they have some security vulnerability in it. So there could be completely different views on your system. It could be just a list of million devices, or it could be all their geographically combined, all the version combined, whatever it is. And with actors, you somehow get the beauty of being able to model these different things. And one concept that you often will see is to use a kind of a digital twin that is representing a thing that is out there somewhere, for example, a hardware device, and this is represented by an actor within your actor-based system, within your Orleans cluster. And so if you then on a higher level have to do something with these devices, you do it with the actors instead, and the actors know all the different ways of communicating to the different parts of the world, to the different models, to the different firmware versions. And you have a nice layer of abstraction and can then on that level use a different way of clustering for each of the problems. So you might think of slicing it in different dimensions, as we already mentioned. And usually what you then do is to build up a kind of a hierarchy of the different devices so that it makes sense to your problem at hand. All right. So I think now we have the tough question to ask. So do you want to see an awesome demo that will be totally
awesome and mind-blowing?
Yeah, or just go with pizza and beer and we will show the demo for the one that are interested, because we are now, I think, pretty late in time. Demo. Okay, that's what we feared. That's going to be awesome, yeah? Okay, demo time. So,
we have prepared a few applications for you. We are talking about distributed systems, and distributed systems are not necessarily need to be complicated. So we thought we just make a simple system. There's going to be coming some sequence diagrams that explain how super simple it is. Yeah. So what we thought, since we're both musicians somehow, we had a frequent problem. We wanted to know the BPM, so beats per minute of songs that we had been listening to. Since playing alongside the songs really makes sense to have the BPM in mind. So we have Eric here, and Eric is absolutely able to clap his hands. So we implemented a very simple Python application that captures the microphone input and basically detects every clap that is done by Eric. This Python application will then forward an HTTP request to a frontend. As we've seen it beforehand in this big picture of system of actors, we have frontends in front of our silo, so we can nicely remote into the system. And then in this silo, we have grains, lots of grains. One for each of the users that are going to use our applications. So far the idea. What these things are doing in detail, I guess it's a little bit too much to tackle in the overview section, but yeah. And then on the other hand, we have also some kind of output. So we really want to know what the BPM is that Eric was clapping in. So here comes Raffi, and Raffi uses a super awesome UI written in React. And this one is then connected to, once again, a backend for this frontend, interconnected with SignalR, so basically WebSockets. We just wanted to put some Microsoft things in there since it's a .NET meetup after all, right? And this is not the end of the story, because as soon as Raffi then enters his name into this lovely UI, this will cause a registration at the backend for the silo. And this...
Sorry to jump in, it's not Raffi's name.
Also, it's Susie, you're absolutely right. Yeah. But Raffi is interested in Susie.
Yeah, sure.
Yeah. Can we cut this out of the recording?
Already in the cloud.
In this cloud. Okay. But we're very closing very soon. So then we have a grain, and this grain responsibility is to notify our lovely web app that the BPM changed as soon as Eric clapped. Doesn't sound complicated at all. Let's demo this thing.
Now it gets complicated. Okay. Here is it. It's the awesome application.
Okay, so to get started with, we might be interested in starting the front-end applications first. So we probably start with the web API. So this is this lovely component where Paul is typing.
Okay. Oh, no, sorry, that's the wrong one. It's the .NET one, yeah. It's just .NET Run.
What does this mean?
What does that mean? Okay, that's a thing for another talk.
.NET command line works 3 hours. Okay, so now that we have the web API started, we might also be interested in starting our Silo application that hosts our lovely BPM detector grains.
Let's do that. I'm typing in .NET Run.
Okay. Actually, he's typing D and Run.
Yes.
Because he has this cool...
Totally for aliases, yes.
Now we could refresh the front ends, I guess, just to be on the super safe side. And
For the real hard thinkers, the spies running here, we just have the development server of the React app is not spawned. It is already running.
okay, and then we have prepared 2 applications. So we have one clapper application that is responding to claps that are clapped into this microphone. Not this, this. And then we have a second application in case the demo failed. No, of course, the demo wouldn't fail. That basically acts on keyboard presses. So you can press any kind of button and that will trigger such a tab event.
Okay.
So we can start with applications, and these applications will then prompt for our awesome names.
Okay, so I'm typing here Python 3 space main.py. Okay.
No, it was .NET Run. He was mistaken.
So, who is clapping? It's Eric, I guess.
It's Eric.
Yeah, sure. I like that some of you got the joke.
It did.
Eric.
I still like it. Okay. So .NET Run for the 3rd time. Should I make it bigger? Okay, so this is Susie, is it? Susie, cool. So, what's next?
We could tap.
We could tap, okay. So, I am Susie. Tapping.
And coincidentally, nothing is happening because we haven't yet subscribed. So it was just a test if you had a very close listen to what I said before. So we're going to subscribe to use Susie.
Okay. Now, give me the beat.
And coincidentally, we're now subscribed. And what Paul previously tapped
Isn't
was
that awesome?
140 BPM. Right. Good. But now we're really interested in the very tricky part about recording the microphone.
Okay.
And this is the...
Let's subscribe to Eric.
And does someone want to come in front and clap for us?
You can do it.
I can do it.
Yes.
Okay. Wait a second.
Isn't this amazing?
Uh-huh.
Can you see?
Okay.
And to support the idea that it is a distributed system, this is Chrome and this is Firefox. And it's really working.
Yeah, there was a demo. Now let's have a look at the actual interactions that are ongoing. Any questions so far? Someone still wants to clap? The demo is running. Just saying.
Okay.
Is it really just random claps on everything?
Sorry?
Is it just random claps on everything?
It reacts on everything. But otherwise the Eric Clapton joke wouldn't have worked, so we decided to clap.
It was good to explain it the second time.
Should we jump into the sequence diagram, or do you want to see the code straight away?
No, you're totally right.
Show me the code.
Show me the
Show me the code. Maybe just have one look at the sequence diagram, just to prove the point that the system is not complicated.
It shouldn't be really in vain that we draw this or roughly draw this. But where is it? I don't have it anymore. Where are my Chromes? Here we go. So let's go to the overview first.
We have discussed the run through, I guess. Anyway, the idea is just that here this user then connects to this web app. The web app forces the user to enter the username. This then again connects to the web API hosting this web app using WebSockets, or actually similar and therefore WebSockets. As soon as the subscription is taking place, we are entering the world of our silo, where we have an HTTP API in front that does nothing except dedicating it to the corresponding brain. And this thing here is this user subscription grain that takes care of really handling all the subscriptions that are coming from this end. The only thing that this grain then has to do is to remember the webhook query. That effectively means it's keeping this in memory as state more or less. And once this is happening, this user subscription grain then goes to this tab input grain. And the tab input grain is this grain that's taking care of detecting the frequency of our clapping. And we use a subscription and notification mechanism here. So this user subscription grain subscribes on changes on this tab input grain. And for the tab input grain to have some kind of flush interval, we then come to this tab input sidecar grain, which is just a timer that fires cyclically every 2 seconds. Good. So maybe we jump to the left side of this chart, where we basically come into the input applications, so our clapping applications or tapping applications, where we once again are forced to enter our name, otherwise the whole session conclusiveness wouldn't really work out. So we have to enter the name, and effectively it should be the same as on the other end. And then we can start clapping. And each of these claps that are recognized through some super advanced machine learning and artificial intelligence promised, will then be HTTP putted to this tab input grain, where we once again have an HTTP API in between that is receiving this HTTP request, and then the sole responsibility of it is to delegate it to this tab input grain. And the first time we actually recognize a clap on this side, we start this timer grain. And this timer grain then fires every 2 seconds and calls a flush operations tab input grain. And this flush operation, basically on timer tick, forces a recalculation of the BPM, which then gets modified all the way back until it reaches our user that is hooked into the awesome React frontend.
Thanks for that, awesome.
Then, how are we timing this?
Time to go to the code, is it?
Awesome. That's exactly what I wanted to hear. So maybe we can start with the controller, the tab input controller. So this is basically the part that's taking care of receiving the HTTP requests from our input applications or from the clapping applications. One thing that we see here is, of course, that we have a very simple action that is receiving the HTTP request. It does really nothing except from retrieving the user ID from the URI, and then it does also the log coincidentally. But the interesting aspect here is the part with the grain factory. With the grain factory, Orleans provides mechanisms to remote into a silo. So we get the possibility that we can reference the grains that are hosted in the silo. And here we basically say, lovely grain factory, please give us a grain with the user ID as an identifier of that grain, and the grain should be of type iTab input grain. And if that grain didn't exist beforehand, Orleans, of course, will make sure to instantiate it on the fly if it's needed. And then, just following up on this, we call this tab function, and then this tab function will just persist that the tab has happened in this input grain. So, yeah, absolutely. If we have a look at our grain, this tab input grain, we basically just are interested in the interface. And what we see here is basically that we have our tab operation that can be called without any parameters. Then obviously we need some way of deriving the frequency from the number of tabs that we have entered into this application. Therefore, we also provide a functionality that is offering the frequency based on the number of tabs. And then for the concern of fulfilling the user subscription grain requirements of subscribing, we also have 3 functions here. So we get the possibility to subscribe another grain that implements this iFrequency change subscriber interface, 2 changes of the frequency in this input grain. We also have the possibility of unsubscribing, which is definitely used here. And then we have another function, this update all subscribers function that is called by the timer, that is ticking every 2 seconds. So this is exactly what's going to happen in this screen, and maybe we jump into the update all subscribers function.
Maybe to make it even more interactive, we could ask the audience a question. So what What part of the solid principles are obviously violated here? I really like it. No, it's obvious, or is it?
Interface integration.
Right, exactly. Sure.
I just said it because it's an interface.
Yeah. Nothing else. Okay, nice. No, but the important thing that I wanted to stress here for the programming model of the all-ins communication. So you see every method that you expose on the grain has to be asynchronous. So there are no synchronous calls. So everything has to return a task. That's
all these methods are used by the same consumer, right? So they are kind of provided to one class which uses all 5 of these interfaces.
No.
Right?
No, that's not true, because the tapping comes from the tap input, and the whole subscription part comes from the React frontend.
Oh.
Question here.
I have a question. The grain is the actor, so all these methods are actually messages that come to the grain, and then are forwarded to the method. Is it correct, or what?
The message aspect of this is really not given, as all the functions that we have written down here are not taking any parameters. If we would really have the message that we pass along, we would see something like this, where this function here takes a parameter. This is how all-ins treats messages. Of course, under the hood, also if there are no parameters in such a function, some remoting call has to happen. So there is some wildcard message that passes the inbox.
And so, for example, if you take a look, what are the implementers? You see the one implementer that is really implementing it. So that's, I'm sorry, what the usages. You have the tap input grain that's really implementing it. And then here you see what all-ins is doing under the hood. So all-ins, for the communication to be possible, is source generating a proxy. So you are talking, of course, not to the real instance of a class that is somewhere running on the other side of the world or wherever it is, but you're talking to a proxy. And all-ins then takes care of all the communication aspects that has to be fulfilled to really communicate to the instance that is running somewhere else. So now we go into it, isn't it?
Shall we?
We shall.
Right.
No.
So this is where we came from.
That's where we came from, actually.
And I think here the tap function is just to visualize that the functionality in such a function should really not be that big, should really keep it sleek and to the point. But I guess what would be really interesting to show is the onActivate function. So we have been talking about this life cycle, and we also have been talking about the fact that this input grain here relies somehow on this timer grain that is disaggregated. And also this timer grain needs to be started somehow. So what we have been doing here is basically using the onActivate function. So this is the lifecycle event that all-ins hooks when we try to instantiate an actor. And we took care of actually instantiating the grain that is triggering us, this timer grain. So once again, we just rely on the grain factory. We get a grain of the interface iTab input flush timer grain, yeah. With this get primary key string, we effectively get the identifier of the current grain we're executed. And then we just call the two functions, register for flush, and then we pass ourselves a reference of us to that grain, so that later on this timer grain can refer back to us. That is, I guess, a very interesting concept there. And the second aspect that we're just doing, we're setting a flush interval, basically telling this timer grain in which interval we should basically send this flush.
Does this register for flush, is this the same as the subscribe mechanism, right? Or is this something different?
Similar. So this, in this case, we have implemented it ourselves, but there's also subscription notification mechanisms with servers in all-ins built in.
Ah, okay. But basically, you are sending a reference to the source grain, to the target grain, so that the target grain can later call back to the source grain.
Exactly. Maybe we can just jump into the implementation. I know Paul is really happy for pizza.
Yeah, getting hungry.
So basically, all that we have are these two functions that we actually wrote here and that we previously called. We have the function register for flush, and there we just pass this thing along. Orleans uses this then as a reference to which grain we should call back. And here we use the holding state mechanism of an actor, where we have one that you can just draw up private read-only field, I guess. I don't know read-only, of course, but it's holding the grain state there. Exactly. And then for the set flush interval, all that we're doing is basically registering a timer. And this is a function that is built into Orleans. We give the timer how often it should flush. So basically that was what we have been passing alongside. It was 2 seconds in our case. And then we provide some asynchronous callback that takes care of, that is executed when the timer takes more or less. And here in this case, we use the reference that we have stored beforehand, verify that it is not null, of course, and then update all the subscribers that are potentially subscribed to our tap input grain at this stage.
By the way, side note from the trenches, this is the part where the single thread guarantee is not fulfilled in Orleans. So the timer callbacks can come in asynchronously. So, yeah.
Is this an Orleans timer?
Okay. Even though under the hood it uses just the classical government timer.
So it's one of the two mechanisms that Orleans provides to do things regularly. So for longer things that might also fail and be restarted again, there's a thing that's called a reminder. So for longer things.
And why did you delegate this sidecar grain? Just because it's cool, or
just so we have more grains to demo, and also to have a scenario where we can actually pass a reference.
Yeah, but
it would be perfectly fine if we would have implemented the timer into the grain. But as we've seen, it was quite stuffed already with things.
And I think the thing we talked about, so in our real system that we are working on now for over a year, we also have that concept. And then also this kind of timer for all the resilience and all the things that you put into it to really make it production ready, it still gets additional code to it. And we have there, for example, the possibility to really decide, do we want to go for the timer route? So this is the thing that you set up, and if something happens, if the grain dies, the timer is away. You have to re-register it. Or if you want to go to the reminder way, that is the more resilient part, where you also can have longer time frames. So for example, you could have a timer for every 5 seconds or 5 minutes, it's totally fine. But if you need something to remind you every 7 days, for example, a reminder might be better. On the one hand, because you can have longer time spans, and on the other hand, within 7 days, it's pretty probable that you won't have in 7 days another instance of this grain, not that very instance anymore. And so you have to kind of re-establish this timing mechanism. And that's what reminders are possible to do. So and if you put then this concern just to a simple single grain, it totally makes sense just to have this, however it is configured, call me back if it's time to do something. But I don't want to care about all the details and mechanisms. It's just on that timer cycle grain.
As you said, Orleans cares about activations. Where is the wire up between the interfaces and the concrete implementations? Is there like a startup config like it is in ASP.NET Core? Yeah.
It depends injection basically. So
and just have a look at the programs, yes. The idea is that you're just using the service connection, dependent injection mechanism that was not provided out of the box, and then it's the wrong program.
All right, we have more to
our nice stepper application. And then we just provide interface to which implementation to bind to, and we just add it with the transient dependency collection.
And usually you then take use of Scruter or whatever to make it automatically and scan the assembly for all the grains that you might have. But basically it's a registration. And we had lots of fun last week.
Yeah.
Is pizza already here?
But we have one more question.
Okay, sure. Go ahead.
This is the, I mean, obviously this is a distributed system in a monolithic data, in a monolithic repository, right? So it's not monolithically deployed, I guess, right? So if you change a single actor, then only this actor is deployed, right? This probably leads to the complexity that if you, I don't know, a breaking change there, I don't know, your task response is different, then probably your other stuff is breaking. Does this framework kind of help you there, or do you just need to stay backward and forward compatible all the time, or what is, how do you do this there, or do they have some analysis of saying, okay, if this changes, I'll do deploy this actor and stuff like this?
Basically, the Orleans people had a very good, let's say, insights or copied some of the concepts. They had API versions already available in ASP.NET, and they basically mimicked exactly the same thing. So you can provide attributes on top of each of the implementations that you provide and pass this versions. So this is version 1 grain. And then the caller could then decide, do I need a version 1 grain, do I need a version 2 grain, do I need a version 3 grain?
Okay.
So this is the way how you would do it. But under the hood, basically you just provide different grains. And
So
this
these will keep the old version great as long as someone uses them.
yeah, if you have them in code and if you have them loaded this way, then effectively you can instantiate them. And if the caller especially decides for version 1 grain, the version 1 grain is instantiated.
And how do you ship this? In different silos, or how do you do it? How do you say cluster you have version 1 running and now you want to ship also version 2? How do you do this? Isn't it the same process?
No, it can be the same process, but in reality, this part, so this dependency injection mechanism runs for all the instances of the silos. So it is not only a single silo that has these grain ones running, but all of them have the same manifest. And as soon as the silo receives such a gossip request to instantiate a grain, then it really just takes a look on what of the implementations is available and instantiates it based on this.
But there is no like dynamic assembly loading and stuff, right? You have to stop the application,
yes,
copy the new DLLs and start it again.
Exactly.
Thanks.
Yeah, sorry. Yeah, but you could have a blue-green deployment strategy. So you have your old cluster running, you build a new version, you deploy a new version of your cluster parallel to the old one running. So you have your old clusters having references to the old implementations, the new cluster, and clients referencing this would create instances of the new one. And then you have to transition over someone, but that's an operation topic that you have to cover there. That's not something that Orleans provides you.
But still, you can only deploy a whole silo when it comes to
Yes, but so the deployment unit, of course, still is the assembly. And if you use the same assembly to provide all the grains that might be needed just for this silo and this silo, it's just up to you. So you, of course, don't have to use all the instances that would be available or the classes that would be available in this assembly. So it's just a matter of how granular do you need the deployment.
I think what makes it easier, Microsoft recommends the co-located hosting of your silo as well as your web API. And if you build your application, you usually update your web API as well as your silo. So no client will reference an old grain because you have the web API in front of it, that this one takes care of which version you want to get out of it. So if you just shut down the silo and run and start it up again, you will always be up to date there. There will nothing be in memory of the old stuff. Of course, you're not zero downtime then, but this makes it a lot easier for the deployment scenario.
Question about frameworks. So you mentioned Orleans, you mentioned Akka, there's also Akka.NET. Do you have short pros cons, what to use, when to use what?
I think it really boils down for Microsoft Orleans whenever you try to be cloud ready, whenever you don't care so much about the details. Akka is more or less coming from the in-memory actor paradigm. So basically, they don't fully support this out of the box, that you have these clustering mechanisms. So it really provides an in-memory tree in the simplest sort. And if you really want to extend it for being cloud ready and being able to scale in that scale, then you should probably go for Orleans. If you want to be fast, of course, then go back to Akka, as it's mostly focusing on in-memory.
So Stan is wondering if this example is available on a public repository.
Is it, Paul?
Not yet.
Okay. Could you perhaps afterwards put it into the meetup discussion? Excellent. And is it a good idea to use Orleans, for example, inside a Unity project? Sebastian takes that Orleans is more of a server thing. How much memory does Orleans take? And is it a good idea to run grains on a client?
I think it's not out of the box a bad idea, but you would have to think what the benefit would be. But still, why not?
Yeah. Do you have like how much memory does it take? Do you have a
So we had a very simple example of a hello world example in .NET. If you write just for the small right line, it basically boils down to 80 megabytes of RAM already used for just instantiating this application. So if you have a Microsoft Orleans vector, the instantiation of this thing is basically 1 kilobyte less. Of course, you still have the overhead of the 80 megabytes of .NET overhead initially, but if you have multiple of these actors instantiated, then it starts to pay off again.
So, Microsoft says on one page, it's about can count with around 100K of actors per VM, for example. I would have to look it up what it is. And I think you have done pretty exhaustive testing now with .NET, with Orleans 7. What are your numbers now?
Yeah, you can host tens of thousands of grains, of course, depending on size and the state. And you also can have fine grain control over the grain lifetime. So if you know grains are only active for a short time, you can command them to deactivate after you are done. So you can get a lot out of it, but we are processing, 30 million messages a day, running on one silo with one Azure Container App instance. So it can scale. Yeah.
For embedded memories, around 30,000 grains can be active.
Yeah. And you can play around with the scaling then a lot once you know what you're running on it.
So an interesting observation that we made is after kind of going into load testing of our application, that the startup times, for example, can be really interesting. So if things are starting up at the very beginning and doing a lot, so if all of the grain or many of those grains are on startup doing a lot of things, then it can be just really a lot of things that are doing a lot of things at the same time if you're starting up your virtual machine. So you can really see it nicely on there's a Orleans dashboard out of the box that you can use, a NuGet package basically that you can use, where you really can see the timing behavior or how many instances that you have. We could show it for these 7 grains that we have here just to get an idea.
That's cool.
But still it's cool, yeah. So somehow hidden anywhere. No, already. So, but it's.
On the same port.
You have
5 something.
Yes.
Dashboard. I think it was Chrome that you had been using.
Right. Amazing, that's what I'm looking for. No, don't care about Jira. Slow close. Was it 5?
There is 56 and then the dashboard.
Right.
Chat again.
Okay, so this is the NuGet package that you can just with 2 lines of code use in your silo, and you have a pretty nice overview of what's going on in your silo. So you see here out of the box the number of grains that you have. You see the latency. That's the orange line that you're seeing here. You get listing the methods that are called between grains with the highest latency. you can get in hands on the methods that are called the most, and then you can go into more details about all the grains that you have. In this super simple example, it's just a handful, but you can see how they're behaving, how much pressure is on each grain, and over time you can really nicely see what's going on in your cluster. And what we observed here is that on startup, basically, it could be that the system is running mad for 2 minutes, whatever, until everything is basically coming up, and then traffic and latencies are going down, and then you are going back to normal operation. So this might be a thing to consider, that how to manage the startup time and the startup behavior, be it on an implementation level, so that you make a stage startup maybe, or we also thinking about using burstable VMs on Azure, for example, so that we can really have a machine that is actually capable of doing this high pressure in 2 minutes, and then going back to normal operation in smaller footprints.
We can answer all the other questions at pizza, right?
Yeah, okay.
Thanks a lot.
Okay. Thank you.
So, one moment before pizza. I tried to be quick. So, and the scan. No. Good. So, only quick. So, thank you, Paul and Raffael, for the talk. As every speaker, you also get some custom-made coasters with our logo.
That's awesome. Thank you very much.
Thank you. This is the time. Yeah, again to you all, thank you for joining here in person and on the stream. Thanks to our sponsors, for Square for the location, for Rubicon and T-Table for financial support, JetBrains for the license. We quickly do the raffle online, so Stefan, please, who won? You would see a nice animation, but I started on the wrong PC, so you don't see it.
Jose J. Jimenez.
Please comment us and his email address, and I will send you the license in the next days. Yeah, if you also want to host a meetup, or your company wants to also talk with us afterwards, next meetups, we have some. Is next one is March 28th. It's about minimal APIs by Purnima. I hope I pronounced it correctly. This will be remote only. And in April 11th, Roman Jacek will talk about Maui. It's not still completely 100% fixed what from Maui, but and this will be an in-person event again. And yeah, we have some echo. Okay. Please spread the word that we are doing these meetups, invite colleagues, friends, customers, everybody. And yeah, we are everywhere. Again, the links to YouTube's like Twitch, Twitter, and website. And one thing that's really important for us is we want to improve these meetups. For that, we need feedback. It would be very cool if you could fill out the feedback quickly, and that we are able to make these events better. And with that, I say thank you, and pizza and drinks. It's where? Where should we go?
This direction, please.
This direction.
Ich brauche eine kurze Hilfe. Ich habe mal gemutet. Ich will noch kurz, ob ich den Namen nicht richtig in den Chat getippt habe. Ja, ich habe da geaddet. Okay. Dann.